Alright, welcome back. Math 1910. We are hitting Chapter 1, Section 3. I think you guys will be pretty successful in this one. We're going to evaluate limits analytically. Alright, so we're going to use properties of limits, different strategies that we're going to imply here. One's dividing out, the other's rationalizing, and then lastly we're going to understand what the squeeze theorem or the sandwich theorem is as we go through this. Okay, so remember from last lecture, all right, the limit of f of x as x approaches c equals f of c. So the first thing we're going to do, as long as the function is continuous at c, right, which means we don't have division by zero, we don't have any holes or anything like that, it's not an absolute value being divided by something, it's not an irrational function, okay, we can just do direct substitution for whatever value of c is and substitute it into the function. Okay, so the basic properties. So what you guys might want to do as we go through all the chapters, all right, in your running notes, I would have all the theorems on one sheet of paper, just, you know, separated out so that you can reference each and every one of them as you go through. Okay, so if we look at Theorem 1.1, there's three pieces to it. The first is the limit of b as x approaches c equals b. b is just a constant, it's a number. So the limit of a constant as x approaches whatever is going to be that constant. Okay? The second one, the limit of x as x approaches c is c. Right? We're using direct substitution there. So whatever value we have for c, so if c was like 5, we would substitute in 5 and the limit would be 5. So whatever value c is, when we're directly substituting into x, it's just going to be the limit. C will be the limit in that case. Okay? And then the third case, we substitute c in for x. Alright, the limit of x to the n as x approaches c is just c to the n. So direct substitution once again. So the one that, you know, gets people the easy one, it's the first one. It's just the constant, so you don't really even have to do much for those. So let's do, you know, here's evaluating the three basic ones that we just went through. All right, so the limit of 3 as x approaches 2 is 3. Okay, there's no substitution in there. It's whatever that function is. If it's 3, if it's 10, if it's 20, okay, that would be what the limit is, because it's just a, you know, a horizontal line that goes on forever. All right, let's look at b here. We have the limit of x as x approaches -4. Well, we would directly substitute -4 in for x, all right, and our limit would be -4. Very simple there. And then the last one, all right, the limit of x squared as x approaches 2. We're directly substituting in 2, so 2 squared would be 4. So very basic here when we're evaluating limits. Okay? Make sure that you have all these properties down. We're going to go through examples, okay? But, I mean, essentially, if we have a scalar multiple that's just like, you know, geometry, things like that, whatever that multiple is, all right, times whatever the limit is. So, in this case, our multiple is b, so it would just be b times whatever the limit comes out to be. Same with the sum or difference of two functions. We would either add the two limits, all right, where L is the limit of f of x, and k is the limit of g of x as they both approach c, as x approaches c for both of those. Same with the product, okay? We could take the limit of f of x as x approaches c times the limit of g of x as x approaches c, and we would be able to multiply our two limits right there. Same with the quotient rule, all right? The limit of f of x as x approaches c divided by the limit of g of x as x approaches c, all right? Once again, the limit of f of x is L, the limit of g of x would be k, all right, as long as k cannot be 0 because we would have division by 0. Same with the power function, all right, we would be able to take the limit to whatever that power is. Very similar to just all the power rules that we do with functions in general. So let's take an example here. How do we approach the limit of a polynomial? This is a case where we can just do direct substitution. Technically, we can break this into two different limits as well, right? This is a sum. So our first approach would be, you know, taking the limit of f of x squared as x approaches 2. And that 4, right, that's our scalar. And then we would have plus the limit as of 3 of x approaches 2 as well. So, or, for me, yes, you can break it down into those chunks, but it's the same thing as if we just substitute in 2 for x, and we get, 2 squared, which is 4. 4 times 4 is 16, plus 3, 19. It all works out the same way. But if you apply the properties, you need to break these into their separate limits. All right, and rewrite that as the limit of 4x squared as x approaches 2 plus the limit of 3 as x approaches 2. And evaluate each one that way. All right, we're using the scalar in the first one. All right, so it's just 4 times 2 squared plus 3, still ending up with 19. Do you need to rewrite it this way? Not necessarily, right? With a polynomial, we can substitute in right away and evaluate and get 19. So that's okay, but it's understanding the basics of how you apply these theorems that allow you to do the direct substitution to get the answer of 19. Okay? So whatever we get for that polynomial, we can directly substitute in. Okay? So if we have the limit here as x approaches 2 of p of x, and we have p of x as 4x squared plus 3, we're simply substituting in the 2. Just like what I talked about. Okay? Direct substitution is valid for all polynomial and rational functions with non-zero denominators. Very important there, non-zero denominators as we go through this. Okay? So let's keep moving. This is theorem 1.3. If p is a polynomial function and c is a real number, then the limit of p of x as x approaches c is equal to p of c. That's just saying that we can use direct substitution to find the limit of the function. Okay? Same with if we have a rational function below, as long as we don't get division by c in the denominator. So you can write both of those down, but we'll do some examples here. Okay, so if we have a rational function here, we have the limit of x squared plus x plus 2 divided by x plus 1 as x approaches 1. Notice when we substitute in for 1 here, the denominator does not go to 0. Good, very good for us. Means we can use direct substitution. So everywhere there's an x, we're going to replace it with a 1. Okay, so when we do that, we end up getting 1 squared plus 1 plus 2 divided by 1 plus 1, which ends up giving us 4 divided by 2, which is 2. So this works as long as our direct substitution does not yield a 0 in the denominator. If this problem was as x approaches -1, we would not be able to do direct substitution. So very important there, direct substitution would not have worked if this was as x approached -1 because we would have division by 0. There's other techniques that we'll use to solve those types of scenarios. Okay, another theorem 1.4. So if we have a radical, okay, so if we have a radical function, we're going to take the same approach. All right, we can use direct substitution as long as c is greater than 0 when n is even. Okay, very, very important. It works for all c when n is odd, so if we have an odd root, but n has to be even. Why is that? Because we have to make sure that we don't have a complex or an imaginary root. Okay, we don't want to end up with a negative square root in this scenario. Yes, that will work later on, but not for what we're learning right here with the basics. All right, so we're not going to have anything in terms of I. All right, so this theorem works when we don't have complex numbers involved or imaginary numbers. Okay, same direct substitution here. Composite function, and once again, we're just breaking down all the properties from a few slides ago and going through each one of them. Okay, so if we have a function that's f of x, a function g of x, all right, and we have the limits for each one of those. When we do a composite function, we take the limit of the inside function and then we substitute it into the other function, okay, the function of a limit. So remember, composite functions are where we're putting one function inside of another function, all right, and getting it out, okay? So let's do a couple examples here. We have two different composite functions. It doesn't look like a composite function to you, but it is. There's a function of x squared plus 4, and then we're taking that x squared plus 4 and we're putting it into the square root function. So it doesn't look like, it's not an f of g of x or g of f of x sort of scenario looking to you, but it is a composite function. Same with the other one, right? We have 2x squared minus 10, and we're doing the third root of it, composite function as well. Okay, so we can do direct substitution on the first one, right? The limit of the square root of x squared plus 4 as x approaches 0. If we substitute in 0 for x, we don't get any invalid values, we don't get any negative values or anything like that, so it's going to work. And we'll substitute that in, and we'll get the square root of 4. The square root of 4 is 2. Okay, next function, we substitute in for x, so you'll have 2 times x squared, so it'll be 3 squared. Okay, so you're going to have 9 times 2, which is 18, minus 10. 18 minus 10 is 8. Cube root of 8 is 2. Alright, so you'll be able to work through both of those problems. Okay, so this is just, the rationale for going through it. I already kind of talked you through how we would solve those with direct substitution, and there's the values that we would get for those. Okay, so there's for A, and then if we take a look, here is where B is being substituted in as well. So this is just kind of the work of what I talked through, but just doing direct substitution, I think you guys can understand and work through that. Alright, so let's take a look at limits with trig functions. Alright, notice there's nothing special about these. We don't have to use inverse properties or anything along those lines. Literally just direct substitution, so whatever c is, okay, we replace it with x. Okay, so if we have the limit of sine of x as x approaches c, just becomes the sine of c for whatever the value is. So notice all of these we can just do direct substitution. Nothing complicated about these. Later on we'll actually learn the derivative of all these, which has some changes to it. Okay, so let's do a couple examples here. We'll just walk through them. So if we look at example 5 here, we have the limit of tangent of x as x approaches 0. So that would become the tangent of 0. We're doing direct substitution, and we should know from pre-cal 2 that tangent of 0 is 0. Let's look at B. We have the limit, okay, of x cosine of x as x approaches pi. So we have to substitute in pi for an x. Okay, so we can take those two separate properties. So we can take the limit of x as x approaches pi times the limit of cosine of x as x approaches pi. We know the limit of x as x approaches pi is just pi, right? We can substitute in pi for x times the limit of cosine of pi. Okay, so we're going to take pi times cosine of pi. So that's direct substitution, and then we know from pre-cal, right, that cosine of pi is -1, so -1 times pi is -pi. Alright, let's do the last one here. We have the limit of sine squared of x as x approaches 0. So make sure that you write this out separately. Alright, so we're going to take the limit of the quantity of sine of x squared as x approaches 0. So it's very important that we write it this way. Sine of 0 is 0, so we're substituting in 0 for the x. Sine of 0 is 0, and 0 squared is 0, so the limit is 0 in this case. Okay, so there's how we kind of work through using trig functions. Alright, now we have different types of functions that we've been able to definitely do with direct substitution. That does not work with all functions, because if it does not work at one point, so say it gives us some sort of division by 0 at a specific value, we have to have other methodologies for approaching this. Okay, so Theorem 1.7 is for functions that agree at all point but 1. Okay, so if c is a real number, right, that's our x as x approaches c. We have f of x equals g of x for all c except for x cannot be c in an open interval containing c. It says if the limit of g of x as x approaches c exists, then the limit of f of x also exists. Okay, so it works for all points except for that specific one. So we can apply some different rules here. We've seen this example before, okay? So this was in our second lecture when we did section 1, all right? This is the first one, if you remember it. that we talked about doing a limit, and this is where you had to use the table approach, right, and substitute in some values. And as we got closer and closer to 1, what was happening, okay? But there's other ways of working through this problem. So we know, right, we have division by 0 here, because if we do direct substitution, we get 0 over 0, okay, which is a case where the limit, we can't do direct substitution to find the limit in this case. And we do know the limit exists because we've done this problem before. And we know that it doesn't create an asymptote, but it does, however, create a hole, right, at x equals 1. Well, we have different methods for solving this now, right? One is, the table method, or we can divide out, or what we call factor. If you guys remember doing that, the top is a difference of 2 cubes. All right, it's x cubed and 1 cubed. So when we factor the difference of 2 cubes, you can look in the front of the textbook. It has a table that has that. I'll try to make sure that I post that table for you guys as well to do the factoring. Okay, but when we factor that, we get x minus 1 times x squared plus x plus 1 in the numerator divided by x minus 1. Notice now that we do that, the x minus 1's can cancel. Okay, so x minus 1 over x minus 1 cancels and becomes 1, and we're left with f of x, okay, now translates into g of x. Okay, it's no longer f of x because we factored out the x minus 1. It's not f of x anymore. It's g of x. Okay, so now we can do direct substitution with g of x. So g of x is now x squared plus x plus 1. We have to call it something new because it's not the original function. Because if you graph the original function, there's going to be a hole at 1, right? And the value doesn't exist. If you were to graph the g of x function here, x squared plus x plus 1, the graph would look the exact same in your calculator as the graph of x cubed minus 1 over x minus 1. However, there would be a value that exists as 1 there. So those are not the two, those two are not the same equation, but they do have the exact same graph. And it's imperative that you understand that and how we can do the g of x and f of x and how it becomes a g of x function once we factor out. Now we can do direct substitution. Alright, so if we take a look at the two graphs, the original function is on the left. X cubed minus 1 divided by x minus 1, and it has the hole in it. Once we've factored and created g of x, which is x squared plus x plus 1, same identical graph without the hole. So they agree at all but 1 point. So that's going back here to this theory right here. They agree at all points except for 1 point, and in this case, they agree at all points except for when x equals 1. So we can use one to determine the other and find the limit. So now we can do direct substitution into the g of x function. Okay, so x minus 1 over x minus 1, those cancel. Now we can substitute in as x approaches 1 into this function here, the x squared plus x plus 1. Because of Theorem 1.7, they agree at all points except for 1 point. Now when we substitute that in, we get 1 squared plus 1 plus 1, so the limit is 3. And that is exactly what we got in lecture 1 when we did this same exact problem. The limit was 3. But we used the table approach, right? We plugged in a few values on the right of 1 and a few values on the left of 1, and it looked like they were both going to 3. So same type of scenario there. Okay? Alright, so just some basic strategies here for finding limits, right? This one's directly out of the book. Alright? You need to just be able to recognize if we can use direct substitution or not. You know, if it looks like if we substitute in and we get division by 0, we obviously cannot use direct substitution, so we're going to have to start using another method, just like the method we did before. So we can factor, or we can use a table, or a graph. You know, sometimes you can still use a graphical approach to look at it, even if the hole is there in the graph as well. Okay? So, if we do the divide out technique, what we just did, okay, we have to check first, right? This is example 7, so we're taking the limit of x squared plus x minus 6 over x plus 3 as x approaches negative 3. Well, here's the issue, right? If we use direct substitution, negative 3 plus 3 in the denominator gives us division by 0. So we automatically know in this case, and this is going back to strategy 1 here, I'm going to step back for a second, recognizing if this limit can work through direct substitution. Obviously it can't. We put negative 3 in the denominator goes to 0. So this is where we have to factor out. Okay, so we can factor the common, factor out of the numerator here. So if you remember your basic factoring skills, right, it's going to be two numbers that multiply to negative 6 and combine to a positive 1, which is in front of the x value. So you always want to make sure that when you factor it out, you try to factor it so the denominator cancels. Okay, so the numerator can factor into x plus 3 times x minus 2. All right, the denominator can, doesn't factor, but it's going to cancel, right? We have an x plus 3 in the numerator and an x plus 3 in the denominator. Those cancel and become 1. We've now turned f of x into g of x. Our new function g of x is x minus 2. Okay, so this goes back to the last theorem that we were just working on. Okay, so we can rewrite this and say the limit of x squared plus x minus 6 divided by x plus 3 as x approaches negative 3 is also equal in all parts except for 1 to the limit of x minus 2 as x approaches negative 3. Now we can use direct substitution, plug in negative 3 for x, and we get negative 3 minus 2, which gives us negative 5 for our limit. Alright, we can see this graphically here as well. If we look at the original function, okay, and the other function, x minus 2, okay, they're both graphed here. They agree at all points but 1, and that point is at negative 3, negative 5. But we can use it to determine that as we approach x from the left and the right, the limit is negative 5. Okay, another technique is called rationalizing. We did a lot of this in pre-calc. All right, we had to rationalize the numerator, or rationalize the denominator, or multiply by the conjugate. So sort of scenario. The same thing goes here. All right, so if we have this rationalize, we can rationalize the numerator or the denominator. Okay, so in this case we need to rationalize the numerator. So if we have the square root of x plus 4 divided by x, we're going to multiply the numerator and the denominator by the conjugate. So if you remember, the conjugate is the same function with a different operation. Okay, so in this case we have square root of x plus 4, its conjugate is square root of x minus 4. Okay, so we're going to multiply the numerator and the denominator in this case by the conjugate. So we're going to approach it in a problem like this, because looking back at our strategies, if we do direct substitution right away for this limit, we can't, right? Because we have a 0 in the denominator. So we have to multiply the numerator and the denominator by the conjugate. Make sure you understand the conjugate piece of this, okay? So we will multiply the numerator and the denominator by the square root of x plus 1 plus 1. Okay, so it's going to look like this, right? Direct substitution fails. So we're going to multiply the numerator and the denominator by the square root of x plus 1 plus 1, okay, over the square root of x plus 1 plus 1. So we're rationalizing the numerator in this case. Okay, that'll yield something that we are able to substitute into to actually get a value that won't be 0. So now we get this new function here. When we rationalize the numerator, remember you need to FOIL the top first, outside, inside last, so that gives us the x plus 1 minus 1 on top. And yes, the plus 1 and the minus 1 on the numerator can cancel. Alright, so we get our new function here, and that leaves us with x over x. The x over x also can cancel, alright? But you have to cancel the plus 1 and the minus 1 first. Alright, so then we're left with x over x times the quantity of the square root of x plus 1 plus 1. Then our x's simplify. So our new g of x function is this. 1 divided by the square root of x plus 1 plus 1. Now we can take the limit of this function. So we took our f of x, we made it our g of x. So we're going to agree at all points but 1. Okay? So in this case, now we're going to take the limit of 1 over the square root of x plus 1 as x approaches 0. Now when we do direct substitution into this, okay, we get the square root of 0 plus 1, which is the square root of 1, which is 1. So we get 1 over 1 plus 1, which ends up giving us 1/2. Okay? So just another method, rationalizing the numerator. We could have done the same thing if it was in the denominator going to 0 as well. So you can rationalize the numerator or rationalize the denominator. All right, making sure that you're multiplying by the conjugate over the conjugate. Okay, and we can see this also when we graph it. Okay, they are the same at all points except for 1. There is a hole in this graph, and that hole appears when x equals 0. But the limit does exist, and it goes to 1/2. So if you notice, if we were a particle traveling left to right on this graph, and as we got closer and closer and closer to 0, x equals 0, right, we would be at 1/2. If we were a particle traveling from right to left on this graph, approaching 0, x equals 0, as we got closer and closer and closer to x equals 0, our limit would be 1/2. So I just want to reiterate this, from previous lecture, the left-hand side and the right-hand side approaching. So remember, as you go from infinity to your point on the right, and you go from negative infinity to your point on the left, those two have to be approaching the same point, and they're both approaching 1/2. Therefore, the limit does exist. The left-hand side and the right-hand side are both approaching 1/2. Okay, the limit does exist as we go through this. Okay, and we can verify this using the table method, and this is what I was just talking about. As we come towards our x value of 0 from the right, we're getting closer and closer and closer to 1/2. As x is approaching 0 from the left, all right, and literally you're tracing, like your finger from the left to right or right to left, all right, where they meet at that point, that is where the limit is, okay, and it works in the table as well. Okay, the last thing we're going to learn in this section is about the squeeze theorem. Okay, so what does that really mean? That means if we have two functions, we have a function h of x and we have a function g of x, and they both have the same limit at x equals c, and we have a third function f of x that is between h of x and g of x, it will also have the same limit at point C. And we call that the squeeze theorem. It's also called the sandwich theorem, right? Because it's between those two graphs that share the same limit, it will also have the same limit at that point because it is squeezed between those two other functions. Okay, so this is the definition of the squeeze theorem. If h of x is less than or equal to f of x, which is less than or equal to g of x for all x on an open interval containing c except possibly at c, okay, and if their limits exist, so if the limit of h of x as x approaches c is L, and the limit of g of x as x approaches c is L, that means their limit's the same, right? The limit of h of x and the limit of g of x is the same. They're both L, or whatever value that is, right? They both end up being 5, or they both end up being 1. That means the limit, okay, of f of x as x approaches c is also equal to L because f of x is between the two functions h of x and g of x. Very simplistic in understanding, a little bit harder to apply, okay? But graphically, this is what we're doing. I'm just stepping back a slide here. We see g of x, we see h of x, and we see f of x is between those two functions. Therefore, they all have the same limit as x approaches the value of c, okay? So, two very special ones that you need to know, love, and memorize, all right? Make sure that these are on your side notes as you're doing your homework and things like that. Theorem 1.9, extremely important. All right, you will see both of these on your tests, okay? These are given ones, okay? And if we were taking an AP test, I guarantee you both of these are on the non-calculator portion of the test because you need to know these. And these two involve the squeeze theorem, all right? We're going to do an example of the squeeze theorem here in a few minutes, but you need to know the limit of sine of x over x as x approaches 0 equals 1. That one's given because what's going on in your head right now is you're saying, all right, well, Sleddy said, you know, if I do direct substitution here, I have sine of x or sine of 0 over 0. I got 0 over 0 and I have, you know, undefined, you know, x equals 0. Well, the squeeze theorem helps us get around this. So we're going to see that in a minute. So that's why you need to know this one. Okay, no, direct substitution doesn't work, but this is one that you need to know. The limit of sine of x over x as x approaches 0 is equal to 1. You need to memorize that one. Same with the next one. If we have 1 minus cosine of x over x, same thing, right? Direct substitution is going to fail because we have division by 0. But by the squeeze theorem, this scenario works. So the limit of 1 minus cosine of x over x as x approaches 0 is equal to 0. Very important in this section and throughout calculus that you know both of these. We see these multiple times. Okay, they're ones that you just need to know. All right, so how do we apply one of those, right? We have a limit involving a trig function here, so we want to find the limit of tangent of x over x as x approaches 0. Well, great. All right, direct substitution doesn't work because we have division by 0. There's no special case for tangent, right? I'm going to step back a slide. There's only a special case for sine and a special case for cosine. Well, you need to know how to apply this. I'm going to tell you right now. We're going to do the example here that uses sine of x over x, and then on your homework, you're going to have to be able to identify the other one that uses 1 minus cosine of x over x. So there is a problem on there. So how do we approach this problem? Well, we know from pre-calc 2, we can rewrite tangent, right? Tangent we can write as what? Sine of x over cosine of x. Very important that you understand how to rewrite that. And it's really going to change how you can approach the problem here when we do this. Okay, so when we rewrite this, we get the limit as x approaches 0, right? I rewrote tangent as sine of x over cosine of x. But notice I wrote them a little differently. I rewrote it as sine of x over x times 1 over cosine of x. Why did we do that? So that we can apply the squeeze theorem from before, from right here. We're going to use theorem 1.9, number 1, when we do this. So I could have written it as 1 over x times sine of x over cosine of x, absolutely, and then separated it. Since they're multiplied, I can rewrite them this way. So I can rewrite this as sine of x over x times 1 over cosine of x. This really helps me, okay? Because now I can use the product piece here. So I already know the limit of sine of x over x as x approaches 0 is 1. Okay, so when I substitute that in, I'm left with what? And I know, well, I'm sorry, I'm getting a little ahead of myself here, but the limit as sine of x over x as x approaches 0 is 1. Okay, and the limit of 1 over cosine of x as x approaches 0. I can do direct substitution in there, right? Cosine of 0 is 1, so that leaves me with 1 over 1. So now I'm using the product piece here of this problem, so I can rewrite this as the two separate limits, right? I rewrote tangent, and I can rewrite these as two separate limits, so I can write this as the limit of sine of x over x as x approaches 0 times the limit of 1 over cosine of x as x approaches 0. I've already calculated those two values above. This ends up just being 1 times 1, which is 1. Okay? So there's how you work through a trig problem. Okay? Try to get it so that you get it into one of the two properties from 1.9. Alright? Most common one you're going to use is sine of x over x. Alright, and when I say, 1.9, I'm going to back up a couple slides. I'm talking about these two. So try to, when you have a trig issue, try to get it into these two scenarios. Either a sine of x over x or a 1 minus cosine of x over x. As the limit approaches, as x approaches 0 for both of those scenarios. Okay? So very, very, very important that you are able to factor out and do what you need to, or rewrite the trig functions so they work out that way. And then lastly, we can go ahead and take a look at a graph and verify, what it looks like. Okay? If we look at graphically on here, if we take a look at f of x as x approaches 0 from the left-hand side and from the right-hand side, the limit is 1. We can see it graphically. Alright guys, I think this section is fairly straightforward. Maybe a little bit of trouble you guys might have with some of the squeeze theorem and the trig stuff, so make sure that email me with questions, or if you need me to Zoom meet or team meet or anything online as well, or ask questions in class. Alright, but else guys, have a great day, and I'll catch up with you in class.